Recording in progress.
Okay, well, it's the final day. And today, I want to say a little bit more about the derived category, mostly about some more philosophy and a bit more about the structure of the derived category. Just a little bit. I mean, the problem is that there's a lot of details and a lot of things. So we'll only see a little bit, but hopefully it should still be motivating enough. So you can see what's more or less going on with it. Okay. So I'll start by talking about some motivation, some philosophy, I guess. So the idea is that cohomology is, okay, the quote is, cohomology is bad and complexes are good. What does this mean? So cohomology alone is not enough. You really want to keep the complexes. Somehow the complexes have more information than just the cohomology. You want the information from complexes. And so, we see this in topology, right? You can have spaces that are, so there are spaces that are not homotopic to each other. But they have the same cohomology. So, we want to so the derived category sort of keeps this extra information. That's why earlier I said somehow the derived category was this analog of the homotopy category. And so what's another example of this in topology? So also in topology, we define HIX by dualizing the chain, the singular, or whatever, singular chain, cellular, or whatever, chain complex, and then take cohomology, right? But we don't just dualize the homology. So H sub I of X, right? So somehow even in defining cohomology of spaces, you want to have the information of the complex and then extract the cohomology. So stuff like this sort of motivates why we want to sort of keep the complex, but only look at the complexes up to homology, and then okay, this thing about making sure the quasi-isomorphisms are isomorphisms. So yeah. So I guess the idea is like we care about the cohomology, but we also care more, I guess, about the complexes. And so we do this two-step process from before to sort of efficiently pack all this information together. All of this is just to make calculations easier and stuff. It's just a nice, convenient device. So, okay. Philosophizing aside, now we can talk more about structure, I guess. So I will be talking most about triangulated categories. So this is a little, okay, so maybe I was misleading earlier. So yes, I wanted to talk about the structure of the derived category, but really I'm just going to be mostly talking about what a triangulated category is, just because that is what a derived category is. It is a triangulated category. And so seeing it more generally, I think is probably more useful, at least just for an overview. Okay. So let's look at this shift functor on chain complexes. So by this one here in brackets, I denote the functor. It looks like, well, okay, I could have just written this, right? This, so it's written to the right. And it goes from CHA to CHA. And it's defined by, okay, so what does it do? It does what you might have guessed it does. It shifts complexes. So take a complex, you shift it by one. But in which way? So the way I want to do it is, so, okay, I'll write it down and then we can figure out which direction it is. So it's so usually just written like this, right? So this is AI plus one. So to the left, I guess, it shifts all the nodes down onto the left. So you might expect, okay, there's some convenient notation here, right? If I write bracket n, this is just going to be, you compose the one however many times, and if it's negative, then you write you put a -1 up here, whatever. Whatever, right? It's what you think it is. And what should the differentials be in this new complex? They're what you think they are. So D, so okay, how should I write this? So DA1. So the ith map here, which also you can write DA1 down here. It's just DA plus 1. Or, I mean, there's a sign convention. There's a minus there. It doesn't matter. It's just the source that I was reading does this. It's just convenient, I guess, for some calculations that I haven't done yet, but okay. Convention, fine. So it works out, great. And so this is the functor on objects. How does it work on chain maps? Again, it's what you think. It just slides everything down. So on chain map, so okay, so if F is a chain map from A bullet to B bullet, then F1, okay, F1 is, okay, this. It's the collection F1I. That's just, okay, it's Fi plus 1, right? It's what you said. It's what you guessed it was going to be. Great. So, okay. The next idea is what is this cone of a chain map. And so, okay, I should define it and then say what I wanted to say about it. So, okay, I'll just define the cone of a chain map. So F from A to B, maybe I need more space. No. A to B, a chain map. Then you can define this new complex, the cone of F. So cone of F, which is defined by the following. So the nodes are, okay, so maybe I'll omit the parentheses. So cone Fi, the objects here are ai plus 1 direct sum bi, and the differentials are so d cone f I. They're these, well, they're written as matrices. You can, this is just convenient notation. So, and then there's this weird sign convention. So it's a minus d here, whatever. dA I plus 1, and then dBi. And then over here, the chain map F appears. It's I plus 1, right? And does the signature make sense? Does it, hopefully I didn't mess up the indices, right? I plus 1 plus bi to ai plus 2 plus bi plus 1, right? Yeah. Okay. And so there are these usual inclusions of complexes. So B includes into cone F in the second spot, and then cone F projects onto, so A shifted by 1 in the first spot, right? So okay, this is nice. But what is the motivation of this? It's called cone F for a reason. So okay, maybe I can finally draw some more pictures. The motivation is from the cone and topology, the real, more specifically the mapping cone. So I'm just going to draw pictures, and I guess you can look at Hatcher or something to see the details. I don't actually know any topology anymore. Okay, motivation. So let's take K, a maybe cell complex, or simplicial, whatever. Nice topological space. Then form the CK, this cone of K. So cone of K by, well, the picture is what you think it is. You take K and you just put a vertex somewhere else, and then somehow cone everything off. I mean, the picture is very easy for simplices. So, okay, so by by forming a vertex S and coning off. So okay, coning off. This coning off has a actual definition, which I'm not going to give. The rest of K. So okay, what does it look like? So if K looks like this, maybe like this, then CK is okay. I take K again. Here's S. I just do something like this, right? Cone, fine. Then what should happen? This, if you look at the chain complexes, the singulars or simple, whatever chain complexes you like on this space. So CK and C of S. So okay, well, I mean S is just a point, so that one is not a super weird complex, but it ends up being the case that this is equivalent to cone of the identity chain map on C of K itself. So cone as in before, and then this identity map as the chain map. But okay, now it's like, okay, what if, where does this become less or a little bit more complicated? If you have a map F from K to L, maybe it's simplicial or cellular, whatever, nice map, then you can get the mapping cone CF, which is, so this thing, it's the same thing as this picture, except now you've glued the K on the bottom to L. So maybe I shade this in and draw this a different color. So this is L, and this blue part is K. Right, and you just identified the K with its image in L, right? You stick them together like that. And then what happens is this. You get C bullet of CF. Oh, okay, so all of this is like the chain complex version of this. It's like similar to the cochain complex version I have above. So fine. Maybe it's not exactly like what I was saying, but this is motivation, right? So, okay, C bullet of S. And so this one is isomorphic to the cone of the induced map F lower star on the complexes. So this one will go from C bullet K to C bullet L, right? Yeah. Okay. So, oh, okay, why do I even have these cones? Well, so, okay, if A is an abelian category, right? Oh, okay, let me leave it here. If A is an abelian category, you can show that the chain complexes on A are also an abelian category. But then when you mod out by these homotopies, then this K of A is just an additive category. There isn't a way to generally always get kernels and co-kernels. So what ends up happening is that there's a way to remedy this, and this is where triangulated categories come in, but you need this weird cone thing to appear. It's not, I guess, so important exactly what this cone is, but I guess the role that it plays is a little more important. So, okay. So instead of an abelian category, the stuff that I'm going to talk about is what we get. Okay. So diagram like this. So maybe X, Y, Z into X shifted by 1. So this, I'll put an F here, is called a distinguished triangle. In K of A, if, so a few things should happen if there is a chain map F tilde from X to Y. So what? Wait, okay, something is wrong here, but we'll fix it such that I think there may be a typo in this one of the diagrams somewhere, such that there is a, okay, there is a chain map, or a chain, sorry, oops. There's a chain homotopy equivalence. So U from Z to cone of F tilde such that, so now we'll see where the typo is. So we have a commuting diagram like this. So start with the original stuff. And then down here, also X and Y, but I think this should be F tilde, right? Because then you can make this happen. Yeah. Oops. This is identity maps. And then here's our homotopy equivalence. So this to say is that, so U is an iso in Ka, right? So this is isomorphism. Right. So typically in these distinguished triangles, we will just call Z a cone, right? Because up to isomorphism, it's more or less just this thing on the bottom. So, okay. We say, so, okay. So having the structure or having the aforementioned shift functor and these distinguished triangles, we say that K of A has the structure of a triangulated category. So, okay, I mean, a triangulated category has a very particular definition, and you have to actually check all the details, but you can always form, I mean, yeah, you have to check that you can do this, but yes. So I should speak more about what is a triangulated category. Oh, but also, okay, so another remark is that the derived category D of A inherits the triangulated, triangulated category structure from K of A. So the derived category has this triangulated category structure. And so here I'm just going to take off the mask and just speak a little bit more generally about what triangulated categories are. So, okay. T is a triangulated category if it is an additive one, category with, okay, so now two things. It has a shift functor with a shift functor. For sake of convenience, let's just denote it the same thing. So 1 from T to T and distinguished triangles. So it has some specified collection of distinguished triangles that look like, so distinguished triangles. So like before, X, Y, Z, and then X shifted by 1. So I should probably label the maps, since in the definition I want to say something about these. So the distinguished triangle should satisfy satisfying. Am I spelling that correctly? No. Satisfying a number of properties. So first up, 1. So any morphism X to Y can be completed into a distinguished triangle. So I'll just write dt. So dt's. So the dt you get is, okay, something like this. I'm just gonna keep using this over and over and over again. So I'm gonna have that in the clipboard, I guess. And okay, so, well, if now I have a commuting diagram, so like this, I will have 2 of these, sort of. Let me get rid of these. This, 1, 2, 3, 4. Another one. So, okay, if I have like this, where these four maps are isomorphisms, this is a commuting commutes. Goodness, just commutes. Then the top row is a distinguished triangle if and only if the bottom row is a distinguished triangle as well. Right. So that's the first property. Then I could probably fit the second one here. Second property is this rotation property. So I can start with a distinguished triangle. And then, okay, so this is this thing is a distinguished triangle if and only if. Now if I sort of chop off the first part and think about continuing it on the right. So this here should be y shifted by 1. The map here, again, this weird convention, minus the shift of f, whatever. But I mean, you wanted it to be shift of f in some form, fine. So the first sequence is a distinguished triangle if and only if the bottom one is a distinguished triangle as well. So you can always keep doing this, keep shifting it over and keep looking at these four terms over and over and over again. So yeah, it's like rotating the triangle, but you pick up a shift. Okay. So the third property that distinguished triangles should satisfy is that, okay, given a commutative diagram, so like this and like this, and so what should go here, here, here? So, okay, if I have P and I have Q, so if this commutes with the rows both being distinguished triangles, then you can complete maps from z to z prime and x to x prime shifted by 1. Well, okay, mainly it's completing the map. You can find R such that the new diagram commutes. So that's this. So R, and then you can also fill in this, and it would still commute. Great. And okay, the last one is this really obnoxious one. It's called the octahedral axiom. It's sort of miserable to write out in full, so I won't. But how it basically works is that, so you can fit together 3 particular distinguished triangles together. And then if you put them together in the right way, you can form a new distinguished triangle of the cones appearing in the first 3 distinguished triangles. Right, so each one will have some kind of a z term, and then you can make a new distinguished triangle from those in some way. And when you do this, you can draw this picture of like octahedra, and it's like that. That's why it's called that. But I'm not going to worry about it. So yeah. Okay. But why would we ever care about something like this? I mean, this is like a huge laundry list of properties. And the reason is because distinguished triangles play an analogous role to short exact sequences. So the distinguished triangles are analogous to short exact sequence sequences. So, I mean, why do I mean analogous, right? In a triangular category, it's merely just additive. So you're not guaranteed kernels and co-kernels. So this notion of exactness doesn't even exist. But these distinguished triangles sort of still give you a lot of similar properties to short exact sequences, and I'll write down a few of them. They should feel very familiar. So this is despite no kernels and co-kernels in T, right? No guarantee. So, okay. So what's some, I'll write down a few nice things that we have already seen basically, but in this new distinguished triangle world. So if I have a dt like this, so nice that I had this copied. Then the composite of any two adjacent maps is 0, so that's gf equals 0, hg equals 0, and then also, so minus f shifted by 1, h is equal to 0, so on and so forth, right? I mean, you can rotate the diagram, right? So that's why it's like this. So similar to short exact sequence. Well, so far, I mean, in the sense that it's a complex. And then, so the second property, so I'm going to have this and another one down here. And so this is a, okay, well, let me do this correctly. So I have x, y, and z. Then down here, I want a different one. So x prime, y prime, z prime, x prime. So if I have maps like these, so P, Q, R, and P shifted whatever, and this one is a distinguished triangle, and this one is a distinguished triangle. If this diagram commutes, then if any two of P, Q, and R are isomorphisms, then so is the third. Right? What is this called in, I don't know. I mean, you just chase the, I mean, I don't know if I said this for short exact sequences, but this is like a true thing, similar to short exact sequences. You just chase with exactness. But here, this is just true. But the proof might be a little more annoying, right? Because the axioms of triangulated category are maybe a little bit more annoying. You can't just, chase with kernels and co-kernels. I mean, you can't, it's not the same, but nevertheless, this is nice. Okay, what's another one? So if I have a distinguished triangle like this, then F is an isomorphism if and only if Z is 0. Right. So that means, so in 2 above, the cones Z are unique up to isomorphism. Cones are unique up to isomorphism. Great. And then, so, okay, there is a notion of a split distinguished triangle similar to split short exact sequences. I'm not going to write it down. It's like the same. I mean, if you had to guess what the definition is, you would get it correct or very, very close to correct. I mean, there's a little bit more you can say in this setting, but okay, not important. Point is, it's like the same. And so what else is sort of cosmetically very similar? So you can still produce long exact sequences in cohomology in some sense. So, okay, we have to define something. So we say f from T to A, where A is abelian, right? This functor is a cohomological, cohomological functor if for any distinguished triangle of the usual shape. So like this, there is a long exact sequence that you get. I mean, it'll look a little different, but it's just like from before. So dot dot dot. So this first one is f applied to z shifted by -1, and then right this sort of weird connecting thing, right? Okay, I'm not gonna draw a big arrow, but fine. It'll continue. How much space I need? So then it'll continue to fx. Then this first map here is ff to fy. This one is fg, then to fc. I mean, okay, this map here behind the fx, that's going to be some shifted version of h with some sign. So maybe I think it might be minus h shifted by 1, and then an f applied to it, so minus. But okay, don't take my word on it. It's something. And then you do this. So fc goes to, so this is fh here. And then it goes to fx shifted by -1. And the dot dot dot. Right. So sort of this is a very familiar looking thing. And so the Hom functors are indeed cohomological functors. Great. Another example. Okay, so in dA, so that you have the usual cohomology functors for the chain complexes. So the cohomology functors h upper I are each also cohomological functors in the above sense, right? And each one will produce basically the same long exact sequence, right? It's just a matter of shifting whatever. So, okay, no matter. How am I doing with time? Pretty good. So now what is sort of like the connection between the short exact sequences and distinguished triangles? Like you might suspect that in the case of the derived category, for example, you should be able to sort of get the distinguished triangles from the short exact sequences in some nice way. And yes, there is. So, okay, there's this fancy snake lemma. Fancy snake lemma. So, okay, start with a short exact sequence of complexes. So, okay, so f, g, and z to 0 in CHA. Okay. Then, oh my goodness. Then there's this map z to x shift not -1, 1. There's an h that you can write down such that we get the distinguished triangle as the one that we usually have seen. So yes, there's a way to do this, and I'll give you the proof sketch. This might be a good exercise. So, okay. Start by just looking at this. So x, f to y, and then y includes into the cone of f, right? And we wanted to find a map from cone f to z. So you can do something like this. So to z and then back to cone f. And then cone f projects onto x shifted by 1, right? So right, this cone has to happen. Somehow the cone is sort of acting as some kind of kernel and co-kernel at the same time, kind of. It's interesting how this works. So okay, maybe I'll call this theta, and we'll figure out. I'll write down in a bit what the second map is. So theta here. So you can try something like theta. So it's a chain map, right? So theta I is equal to okay, where does it go? It goes from xi plus 1 plus yi to zi, okay? And it's given by this matrix. So 0 and then g to the I, the second entry. So it's like this. Then, okay, so the next part of the proof sketch is to show that theta is a quism. Dt, okay, this dt is in, where is this dt? This distinguished triangle is in d of a, right? This is why this quism thing is coming up. Okay, so it's a quism, and then what is the new map here? You can actually take its right inverse, and then right inverse? Maybe not right inverse. Okay, whatever. I don't know for sure. I have to check the details, but okay. Whatever inverse it is, then you can check that the above, we get the dt as expected. Okay, great. Okay, so what else can you do in the derived category? So derived functors, question mark, where do those, come up? Unfortunately, it kind of sucks. The process is a little involved, but there's sort of a natural entry point that I could talk about. So derived functors. So I need a definition of so-called triangulated functors. So f from t to t prime, so these are both triangulated. So this functor f is a triangulated functor. If, so two things, f commutes with the shift functor. What is meant by that is, when you commute them, the two things you get are isomorphic in a special way, whatever, unique way. And it sends, and f sends distinguished triangles to distinguished triangles, which is apply the functor pointwise ... what you think it is. Great. So I mean, we can just sort of experiment. So if we start with some functor f from a to b, that is an additive functor of additive cats. So starting with just the bare minimum, what you can check is that it passes, so f passes to a functor on functor k of a to k of b. Does that make sense? Can I even talk about the? Yeah, I mean, okay, for chain complexes, I only ever insisted that the two maps compose to 0, and in the case that it is abelian, then you can talk about the kernels of the maps involved, right? So this is still okay. So yeah, I can still talk about this. And so this f passes to a functor on these homotopy categories, which you can check will commute with the shift functor, and it will also send distinguished triangles to distinguished triangles. In particular, what it will do is it will send cones to the right cones. So fine. So f here is f. So f here becomes a triangulated functor. Okay, now some more upgrades. So if A and B above, so A, B were abelian categories. Oh my goodness. And f was an exact functor. So tense. Then I mentioned this earlier. If this is the case, then you can actually commute f with homology or cohomology. So f hn of some complex x is isomorphic to hn of f applied to the complex x, right? So that is to say, you can unpack this, and you can see that so f sends quasi-isomorphisms, so quisms, f sends quisms to quisms. So this will let you pass f to a functor d of a to d of b in this case. And f f on so k of a to k of b commutes with localization. So q from k. Okay, both. Okay, however, I'm not gonna write the signature down, but fq and qf, whichever functors you apply first, there's some isomorphism between the two things you get. So localization functors. Okay. So this was for f exact. You just straight up get, you immediately pass to functor on derived categories. Okay. So f not exact. What should we do? Okay. I mean, it sucks. There's a lot, but you can still get something, and what you get is we call a derived functor. So if f from Ka to Kb is triangulated, define, okay, I'm not define, but there's a way to obtain the right derived functor called Rf, which goes from dA to dB by some involved process. So sad face. If I had more days, this would have been the topic of discussion. It's pretty cool. But basically, okay, so what does this RF do? So RF, uh, RF of X, bullet. So, right, it takes in a complex X, and so what is the punchline? How should I summarize this? Okay, here. So this, what do you get when you apply RF? You get another complex, is a complex whose cohomology is RIF from before. So RIF on X, right? So that's sort of the punchline. So we've replaced this collection of derived functors, RIF, basically with RF. It just takes in a complex and spits out another complex that just contains all of this data. And I guess the punchline is you get a little bit more, hopefully, I mean, by just having this whole complex with you. And so I guess, yeah, that's the punchline. Complex is good, cohomology bad, question mark? I don't know. So yeah, that's all I wanted to say. And yeah, thanks for coming. I guess I should also thank Mark for doing the category theory the week before, so 2 weeks ago. You know, it really helped streamline the process. I didn't have to worry about defining every single little thing. So yeah, thank you. Thank you to everyone. See you next year. And for people who know me or will know me, I guess at UT, see you soon.